first of all, Sinan, thank you so much for putting this event together. This has been just awesome. It's been so great to meet some of you and really excited to meet the rest of you. And I also apologize in advance for talking about quantum physics right after you ate lunch. Just some casual quantum mechanics to digest your food while you ponder. Maybe just by show of hands, and can everybody hear me okay? Great. By show of hands, when I say quantum, how many people know what that means? Great. Pretty good amount. And if I were just to ask you, maybe again, we'll just do a little interactive session here. When I say quantum, what words come to mind? How would you simplistically describe quantum if anyone wants to take a quick crack? Qubit, speed, good. Content, not zeros and ones. Those are all, yes. Two places at once, yeah, very much so. Great. That's all fantastic. And so the way I describe quantum is, and everything everyone just said is true, but when we say quantum at the most basic level, we're talking about the world of the very small. So we're talking about the atomic and the subatomic levels, where there's a whole different set of rules that rule the day. They're called quantum mechanics, and everything everyone just said are basically properties of quantum mechanics. Now, you may have heard terms like superposition, entanglement. These are some of those strange and wonderful things that happen down at the quantum realm, and we don't experience them on our day-to-day basis. They really these phenomena get kicked out of existence by all the noise in the world around us. So they're very counterintuitive, but we just have to accept that they exist. You probably hear a term quantum modality thrown around quite a bit. A modality is just the way you actually go about taking advantage of those underlying quantum mechanics and turning them into products. And our modality is neutral atoms. It's a very flexible modality, and it's got a pretty long history. And it really all goes back to the founder of our company, Dana Anderson's foundational work at the University of Colorado Boulder, where he was part and worked with several Nobel Prize winning teams that effectively figured out the technology that ultimately is neutral atoms. And I first got involved in this business in 2018. Before I became CEO of the company, I was an investor at a firm called Maverick Capital for almost 19 years. And I was the first investor in the company, and then was on the board for the next 5 years, and then got the really unique opportunity to join full time and really focus on accelerating the commercialization of this underlying technology. Someone threw out the term qubit. And what we like to say are atoms are nature's perfect qubits. We don't have to build anything. We don't have to produce. We don't have to manufacture our qubits. They're given to us by nature. All we need to do is we trap those atoms in these ultra-high vacuum cells. And in fact, I have one with me, a little prop. So this is our quantum core. Inside this lives millions of atoms, and each one of those atoms can become a qubit. And there's a lot to like about neutral atom, this particular modality. The flexibility is one of those things, and we'll talk about the other products you can build. But if we're just thinking about atoms as qubits, they have a natural advantage. All rubidium and cesium atoms, which are the atoms we work with, are the same. We don't need to produce them. We just need to harness them and control them with lasers. They're very commercially stable. They scale. You can put huge amounts of atoms inside this little vacuum cell, millions, and that means millions of physical qubits, and we can control them very, very well. And this is actually what Dana spent his career doing. He was an applied physicist, not a theoretical physicist. So you don't get to win the Nobel Prizes, but you build the stuff. And so when I met Dana was running a little side hustle off of his lab, selling these devices to other labs, basically to do neutral atom experiments. And what I saw, because of the flexibility of this underlying modality, was the ability to build a quantum company that wasn't just focused on computing, but actually could be commercializing products along the way based on that same underlying technology. Because, well, atoms are nature's perfect qubits. They also happen to be nature's perfect clocks, nature's perfect antennas, and nature's perfect sensors. And so we sought to build, again, was a quantum company that was creating products that had real quantum advantage today, truly 10 to 1,000,000 times increase in performance, monetizing those along the way to the crown jewel of quantum computing. And you can think of it almost as following the NVIDIA monetization strategy. They had this core GPU, which they first pointed at gaming, right? Graphics processor. They then pointed it at crypto mining. And then ultimately the crown jewel of large language models came along. In our case, we have this core neutral atom engine. We started by pointing it at the clock market, and then the RF antenna market, and then the sensing market, and then ultimately building quantum computers with them. And we built and sold 3 quantum computers to date. And we tie everything we do together with software. And so let's just use a couple of examples. Let's say ticker. How does our clock work? How do we turn atoms into the ticking of a clock? What we do is, remember, we have millions of rubidium atoms trapped in this ultra-high vacuum cell. We then excite them with ultra-high frequency lasers, and we turn that energy transition from excited to neutral, a very, very fast excited to neutral, effectively the superposition of the atom. We turn that into a very stable frequency reference that just happens to tick about 1,000 times faster as traditional atomic clocks. So we take those atoms, we turn them into clocks. Let's look at Skywire, our RF receiver. That same cloud of rubidium atoms can actually be turned into antennas that have magical properties. It kind of turns everything we know about RF technology on its head. Normally, you need a physical antenna that matches effectively the wavelength that you're receiving. And therefore, you need a very different type of antenna aperture for all the different parts of the electromagnetic spectrum that you're receiving. We can actually create ultra wideband antennas made of atoms that can be tuned to receive from the hertz to the terahertz range on something the size of a sugar cube, much smaller than this device actually. That's absolutely game changing. And we'll talk about some specific examples of that and why that matters. Then finally, we can turn those atoms into very, very sensitive sensors that sense forces like gravity. We've had our technology up in the International Space Station since 2018, sensing gravity on Earth's surface to track things like the melting of polar ice caps or the digging of tunnels underground, etc. So a lot of very interesting use cases for quantum today under that broader sensing umbrella. And then finally, those same atoms can be used to build computers. Instead of addressing the cloud of atoms, we individually address each of those atoms, turn each one into a qubit, array them, entangle them, and then perform calculations. And again, calculations that would be very, very difficult for a classical computer to perform, all based on that same Infleqtion quantum core. And given the fact that we have commercialized usable products today, we work with a number of great customers across the national security, the space realm, energy, AI, drug discovery, material science. And as you can see, there's some of the best names in the business, ranging from NVIDIA to Army to NASA, SAIC, and the list goes on. So let's talk about a few very specific use cases for this technology. And let's talk about GPS to start. GPS is a position, navigation, timing system. But in reality, it's a lowercase p, lowercase n, capital T. Not a lot of people know that. Timing is the most important thing that comes down to us from the GPS networks. Many, many critical infrastructure sync to GPS. They rely on being able to access GPS to synchronize. And if they can't synchronize, they can't work right. When we're talking the electricity grid, the RF networks, financial markets, data centers, all rely on access to GPS. And unfortunately, as we keep reading about, GPS is becoming more and more prone to being spoofed or denied. Just a few weeks ago, Ursula von der Leyen's plane was hit with a GPS denial attack. This is happening increasingly in concentric circles out from Ukraine and the Gaza Strip, but more and more happening globally, and it'll only be a matter of time before it's more of an issue here in the US. Our clocks, ticker, can actually provide better than GPS time in a locally, completely unspoofable, unjammable way, such that you have some redundancy to synchronize and make sure your infrastructure can work in a GPS-denied environment. Let's use another example. And this is the RF antennas that I was talking about. Did you know that a Stryker vehicle has, on average, over 10 radios in it? Each one of those radios, for the reasons I said before, requires a different antenna because they're addressing a different slice of the electromagnetic spectrum. And increasingly, those radios are being jammed. This isn't like a future battlefield issue. This is happening every day in the war in Ukraine. So what's been the solution thus far? More radios, more antennas, redundancy. The jungle of antennas grows thicker and thicker. But imagine a world in which you could collapse all of those antennas down to one antenna, the size of a sugar cube, that could be dynamically tuned to receive the entire electromagnetic spectrum. Or better yet, an array of those small sugar cube size antennas that are all dynamically tuned to different parts of the spectrum and emit no signal that's such that you're completely undetectable and are not prone to being spoofed or denied or jammed. It's really the RF communication revolution that the battlefield needs and will ultimately have. And then finally, let's talk about a longer term, more aspirational thing that quantum computing will be able to accomplish. So did you all know, I didn't know this until recently, that 50% of the world's food production relies on one chemical reaction discovered in 1913. It's called the Haber-Bosch process, and it's used to create all of the world's fertilizer. And it's incredibly inefficient. 2% of the world's energy is utilized to do the Haber-Bosch process to make the fertilizer that helps us grow our food. And despite truly 100 years of trying to find a better way, we have not been able to, because computers cannot model this complex molecular interaction. This is the type of thing that quantum computers will be able to help us with. They will be able to run the simulations to find a better catalyst that's significantly more efficient, significantly less energy consumptive, and effectively securing the world's food supply going forward. And so quantum will actually help us figure out the chemistry to make better fertilizers that are more efficient and secure the world's food supply. And that is a similar problem set, just like the factoring of large numbers, that classical computers will have a very, very hard time doing. We can talk later about why that is, and it's really because we're harnessing those quantum mechanical properties to do computation, but we'll park it for now. Make no mistake, this is a race. China is out investing the US by a pretty large margin. But if you look at the US and our allies, we are out investing China. But I believe that both of these lines, red and blue, are going to continue to grow to the right. And this is a race that we cannot afford to lose. The stakes are very, very high for all the reasons I just mentioned. And so with that, I'll just end on this fact that every generation has a technological leap forward. We are all living through the AI generation and all of the changes that are taking place because of that. And Keith did a really great job explaining that in the keynote this morning. Quantum is coming, and it will be that type of leap forward. And the nations that are first movers are truly going to hold the pen of the rules that get rewritten based on this new technology. And so it is absolutely critical that the US and our allies win this race and stay ahead. And it's highly motivating for me to do this every day to make sure that happens. I'm getting the hook. Okay, everybody. Well, thank you very much. And again, happy to talk about quantum anytime.